So yes, let us start. So before actually doing the lab, as I have told, these are some of the fundamentals that I will be covering now. That is for forward kinematics of a serial chain robot. Okay, so that it becomes very much conversant when you actually start doing forward kinematics. For now, my assumptions are that you already know what is a robot, what is a serial robot. Okay, and you have some prerequisite of linear algebra, that is matrices mostly, and vectors. Okay, so yes, here I go. So this is a standard serial arm robot that you have seen quite a lot of time now. So yes, it looks like this. It is link joint, and finally it is terminating at the end effector where it actually does the job. Okay, so standard industrial robots are normally 6 degrees of freedom with 6 revolute joints. 6 revolute joints. At times there may be combination of revolute and prismatic, as in case of Skara at least. Okay, so this is how it look like. Okay, there are many makers for this. You already know Kuka, ABB, Fanuc, Yaskawa, and many others. So today we'll focus on Yaskawa robot because I have that in my lab. I have recorded for that. Okay, so I'll be basically focusing on Yaskawa, but doesn't matter, things goes all the same, theories remains the same. Okay, applications, it can do a lot of pick and place tasks, surface finishing, welding, painting, collaborative, and many similar tasks. Okay, so let us begin about the theory of uh, forward kinematics briefly, because I won't be covering very much in detail. In order to know that in detail, you may watch my video that is precisely on this subject, that is forward kinematics, very much in detail that is there. I'll refer you to that. But yes, let us begin with kinematic structure of a standard industrial robot. As I have said, there is a universal frame. Okay, let me start with the frames first. So this is a frame about which different objects in the industrial workspaces are placed. Okay, so it may be a corner of your workspace, industrial corner, your entire workspace corner. So you have first robot, you have second robot, you have third robot, and many other robots. They all are coordinated and they all work simultaneously on a particular object at times. So they all are to be referred using a single coordinate system. Yes, this is at xy position, x1, y1. This is at x2, y2. This is at x3, y3, and so on so forth. So you may have multiple robots all represented on this frame that is known as universal frame. Okay, but when we talk about just one of the robot, just one robot, so this may not be required. So you can talk directly in terms of the robot base itself, where it is mounted. So let us say it is mounted here. This is known as a robot base frame, or simply the robot frame, about which you represent the end effector. This is known as the end effector, which actually has a tool mounted on it, and that does the job. And sometimes it is the tool tip, which is the end effector, that actually does the job. If it is grinding, if it is a painting, so anything that is done by this part of the robot, that is known as end effector. Here it is represented as E, and end effector frame. So everything, every location which I want to represent with respect to this base frame is a frame. Why it is a frame? Because I won't be just calling it a position in workspace, rather it will be position and orientation. Okay, so let us say you have an object. Okay, so it is not just located at a place, it is oriented in a particular manner. In order to represent that thoroughly, you need to have an a frame which is attached to this. Okay, so that is why it is attached. So it has its own x-axis, y-axis, and z-axis. Okay, so that you can represent that frame orientation as well as location with respect to the base frame. Okay, there are many other frames which may be of importance, like a part frame. This is your part, this object which you will be handling. So this part may be located at some position xyz, with respect to robot's ground frame, okay, where it is attached, where the robot is attached to the ground. So that is the robot frame. You have a joint frame also, about which you have, at least if I say, if it is this joint I am talking about, this is the link which rotates about this axis. Okay, so if this is one of the frame, this is one of the frame, about this frame this link is rotating, about this frame this link is rotating, is it not? So there are different joint frames. So when I move the robot in joint space, it rotates basically with respect to these frames, that is about these axes. Okay, so there are as many number of joints you have, as many number of joint frames you will have. Okay, so that is represented as J over here. Hand frame is basically the flange, robot flange. When it is delivered to us, robot, when it is delivered, you have a flange where you attach a tool. Tool can be a simple gripper, two-fingered gripper, right? So that can be attached here. Okay, so this is the frame on which you attach the tool, and that is known as the hand frame. Okay, so this is your hand frame and this is your tool or the end effector frame. Okay, so these are some of the frames which are very important when we start representing a structure of the robot in a Cartesian system. Okay, in order to define it precisely, okay, how it is oriented, how it is positioned. Okay, so those things are very important. So yes, so now how will you, let us do some coordinate geometry out here, or just vector or matrices way of understanding a point in a space. So this is how a point is represented in a space. Okay, let us say this is a point which has a coordinate of ax, by and cz. Okay, a is the distance measured along x axis, this one. By is distance measured along y axis, this one. Okay, and cz is the distance measured along z axis. Okay, so these are the three coordinates which is used normally in Cartesian space to represent any point like this. We have been doing this way quite long time now. So this is how it can be represented using a position vector also. Hope you know this as well. In case you want to represent this in robotics we normally do it this way. Okay, so this is the matrix. This is a matrix, column matrix, which represents ax, by and cz in a column, and w is the weightage. Normally this is equal to 1 in robotics. If it is computer graphics or maybe multi-body dynamics at times, so normally in case of computer graphics, animation, simulation, w may not be equal to 1. So it is normally coordinate along x, coordinate along y, coordinate along z, and 1. So this becomes your point. This is a point. We'll represent it as bold small letters, bold letter and small. It is not capital letters. Okay, so this is small. So this is how we'll represent any point in space. Okay, so now going to next, if it is a frame, if it is a frame which is attached to an object, as I have said, it will have three axes. It may be a rectangular object, it may not be a rectangular object, but frame is always a rectangular one with three vectors, orthogonal vectors known as normal, orthogonal and approach, or sometimes it is NSA, maybe normal, sliding and approach. Different books have different conventions. So basically what these vectors are, normal vector n is a unit vector along local x-axis of the object. That means if it is a u vector, UVW, let us say if it is attached to this object, so one of the vector is normal vector. Okay, it will have, let us say if it is unit vector along one of the axis of the object. Okay, if this is a frame, so it will have its own components, nx along x, ny along y, and Z along Z. So this will have three components. Sum of those will give you normal vector n. Is it not? So this is how we represent using matrix nx, ny and nz. It is a column matrix, that is why I have represented using transpose of that. So nx, ny and nz is a column with which we can represent vector n. Okay. So yes, that is n. Similarly, you have orientation or orthogonal vectors. So that is ox, oy and oz. So if this is o vector, okay, it will have its own component along x, ox, component along y, oy, component along z, oz. So that is ox, oy, oz. Similarly, approach vector is ax, ay, az. So this is a vector form of that, this is matrix form of that. So altogether, a frame F is a capital bold letter represented as a matrix like this. So this is what? This is vector n, unit vector n, this is unit vector O, this is unit vector A. Okay. So these are three vectors and their projections along x, y and z, x, y and z, x, y and z. These three are orthogonal vectors. Okay. So that represents a frame. So all three combinedly will represent a frame, and this will represent now the location of this frame is the point which is here, that is F, and this is italic capital, this is bold capital. So this is whole of the frame, this is location of this frame. Okay. So location is intersection of all those unit vectors at that point. So that is the location, and these three represents the orientation. So it represents complete information of an object in space, that is position, fx, fy, fz, that is the point, and NOA will represent its orientation. Okay. So yes, now I can dislocate this point from O. I can make this point travel to a distance which is now located at F. This time you have a vector which represents the location of F by vector Px, Py, Pz. So this is a position vector. Position vector. Be very careful when I see. So a position vector, it is bold, small again, and this is how I write it in vector form, and this is in matrix form. Transpose over here because it is a column matrix. Correct? Is the position vector OF that connects point O to point F. So this is the position vector. So that comes at the end. Okay. So overall, in the matrix form, a frame is represented with a position which is here and orientation that is represented by NOA vector, as I have explained in the previous slide. So this is N, this is O, this is A. Correct? So this is how orientation and position together is given by the matrix F as 4 cross 4 matrix. Why it is 4 cross 4? We'll tell you later. Okay. So that is known as a homogeneous transformation matrix. So needs further understanding of translation. Let us understand that first. So now a rigid body, you have seen, can also be represented, not just a frame. A frame may be attached to a rigid body. Okay. And again, you can represent that object as a whole. If an orientation, and I assume this object is not deformable object, okay, it is a solid object. So this is your position, this is your orientation. Okay, this is your orientation. Got it? So this is how an object is represented in space. Okay. So now what is a transformation? Transformation matrix is an operator which is given by 4 cross 4 matrix when applied to a position vector represented as a column matrix makes movement in space. So transformation will move whole of this in space, this object, if I apply that transformation matrix to a location, it will be shifted to another location with certain orientation to say. Okay, so definitely both transformation includes rotation and translation operator. So this is an operator which is acted on a point or a frame, and your frame gets translated and rotated, and this becomes your new point. Okay, so let us see how it works. So it can be a pure translation, it can be a pure rotation about an axis, it can be a combined translation and rotation. Okay, overall it is given as, transformation matrix is given as a combination of rotation. Rotation matrix is R 3 cross 3 submatrix which is responsible for rotation operation, and you have last three elements that represents the, that basically performs the translation operation in three-dimensional Cartesian space. Okay, so this is your transformation matrix. This can be applied to an object, to a frame, to a vector, to force. Okay, for any vector quantity you can apply this, and that can get transformed in space to a new location with a new orientation. Okay, so what are the uses of this? Basically advantages. So it can represent all transformation as a matrix multiplication. Okay, it can capture composite transformation conveniently. Composite means can be a combination of rotation and translation. Okay, conveniently, and it can change the reference frame, it can change the vector in space, it can be used as a rigid body configuration, it can be used as to represent a rigid body configuration also. Okay, so that is what is homogeneous transformation matrix. So now let's see what is translation matrix. So it looks like this. It looks like this. When applied to a point, let us say you have a point in space which is given by px, py and pz. Okay, when you apply this translation matrix, that is pre-multiply this point vector, okay, column vector to this, you get what? This. You can try multiplying this, definitely you will get this. So now what is this? If this is point P, this represents point P dash, is it not? So it is Px, Py, Pz. So this is effectively Px plus Dx, component of D along X, component of D along Y, component of D along Z. What is D? D is basically the displacement. So this is how a point may be translated in space by a displacement T. D, a vector with a component dx, dy, dz. So this is how it works. Similarly, you may have a pure rotation matrix which tends to rotate. When it is applied to a point, it tends to rotate about x-axis. It may be about x-axis, it may be about y or z-axis also. So this is how it will be rotated. A frame, if it is attached to a body and I apply a rotation matrix to that, you will get a new frame which is rotated about x-axis by an angle theta, or maybe by an angle theta by about y-axis or about z-axis. Anything is possible. So you have different matrices for that. Overall, if this is your initial coordinate, PUVW is the initial coordinate, that is the object frame. Okay, if I want to represent this object frame in terms of global frame, that is XYZ, okay, so you have to multiply with this rotation matrix. It looks like this. I won't go very much deeper into it, rather I'll just explain how this works. Okay, so this is your initial frame, you apply a rotation matrix, you get a new coordinates of the PUVW frame with respect to x, y and z. Okay, so this is how. So let us say you want to rotate about x-axis. Okay, so what effectively you get something like this. So this is for rotation of an object. If you want to rotate an object by angle psi about axis x. Okay, so you can take this as x, y and z. If you want to rotate, I'll tell you cos minus sine, sine cos. Okay, cos minus sine, sine cos. It is cos psi minus sine psi, sine psi and sine. So this, if this is for the rotation about x-axis, put this as 0, this as 0. Column and row corresponding to the axis as 0 and rest is cos minus sine, sine cos. So this is rotation matrix about x. Similarly, you have rotation matrix about y. Similarly, you have rotation matrix about z. So if it is about y, okay, you put this column and row as 0 and then you have cos sine minus sine cos. Okay, in case of y, it is not cos minus sine sine cos, it is cos sine minus sine cos. Similarly, if you want to rotate about z axis, so this is z, put column and row as zeros and then it is cos minus sine sine cos. So this is the corresponding angle about by which you want to rotate. So effectively it works like this. So you have to apply this. This is your initial point, this is your new point when it is rotated. So let me see if I can derive it geometrically. Let us say you have a point P, okay, which is at a distance r from origin, that is O. This is your x-axis, y-axis. So initial point location will be, this is your px from here to here. Similarly, this is your py from here to here. This you all know, these are basically projections of OP vector along x and along y. So magnitude of that will be, if this is r, it is, and this is angles phi. Okay, so it is px is equal to r cos phi, py is equal to r sin phi. So you all know this, this is just by projection. Now I have rotated this point about z-axis which is perpendicular to this plane, perpendicular to the plane y xy. Okay, I have rotated about this by angle theta. Initially it was over here, now I have rotated by an angle theta and it has gone to a new location p dash. Okay, now let me see if I can express that once again. So it is px dash is equal to r cos this plus this, is it not? Theta plus phi, theta plus phi. So this is again by projection. So this is your new coordinate. This is your new coordinate. This point, this is the point. So this is py dash, this is px dash. Correct? So this is your new point. Let me see, is there any transformation that brings this point from here to here? Let me see if I can derive it. So I'll just expand this using trigonometrical identity, that is cos theta plus phi. So cos A cos B minus sin A sin B. So you just multiply with the magnitude r which is sitting outside. So this is there. Similarly py, this is expansion of sin A identity. So you get this. Okay. Now I'll substitute px r cos phi, So I will substitute this here. Okay. Similarly py r sin phi, I have substituted here. So equivalent thing that I can write is something like this. If can I express this as a matrix? So yes, I can do it. So let me just write it. Px dash py dash is basically resultant of multiplying with the matrix cos theta minus sin theta and cos theta, and this is your px py. So hope this is correct, you can obtain this. So can you get this? This is simple. You just, this is your transformation matrix for rotation about z axis by an angle theta. rotation about z axis by an angle theta. Okay, so this is what I have done. So this is your px py initial coordinates which was there, px py. If I rotate by an angle theta, what I obtain is px dash and py dash. Px dash and py dash is the p dash location. Okay, so in terms of 4 cross 4 matrix, as we have seen just now, in case of homogeneous transformation, here it goes. So this is 1, column and row is 0, cos theta minus sin theta, cos theta, right? So this is your rotation matrix. This is where it should go. Okay, this is your initial point, px, py and pz. Okay, so yes, now you get this. So this is the rotated point. So what is this? This is a rotation matrix about z by an angle theta, which is when applied with point P, it becomes point P dash. So what happens to P? It gets rotated about this axis z by an angle theta. So it goes to a new location. This is how it is expressed. This is what is the job of a rotation matrix. So now hope you understood what is a translation. This is a translation. This is translation operator can be applied to a point to translate it by a distance. This similarly, you also can have a rotation matrix, which is when applied to point this, you get to a new position, that is p dash, which is nothing but rotation. Okay, so this is how it can be written as. Okay, so yes, so you now know there are operators, which is translation operator or rotation operator, which can do multiple things. So rotation operator about z we have seen just now in this. It can be rotation about y, it can be rotation about x, as we have seen in the earlier slide. This is rotation about x. So these are some of the rotation metrics that I have demonstrated. It can work in a composite manner. You can have a sequence of rotations, okay, one after the other. So you can do rotation, 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 and keep on doing that to a point, and first transformation, second transformation, third transformation, one by one you keep on applying. So this is what will be the sequence of operation. Sequence is very, very important. Okay, you won't reach to a same place with 3 sequence of rotation. Okay, you have to mind this. Rotation sequence is because matrix multiplication is not commutative. A B is not equal to B A. Both are matrix. You see, this is matrix, this is matrix. You cannot write it other way. So sequence is very important. You will reach to a different place, different pose if you rotate in a different sequence. Okay, so that is what is to be noted. So yes, so this is how you represent orientation of any object in space. That is what is used in quadcopters, that is what is used to affect the orientation of any industrial manipulator and effector frame with respect to the ground. Okay, so these are different ways to represent Euler angle system. There are more than 24, almost 24 different combination in which this can happen. This is one of the most popular one, that is representing the orientation with respect to the ground frame. Okay, with respect to the ground frame. So we can rotate about x axis by certain angle, rotate about y axis by certain angle, and z axis by certain angle, and you whatever is the rotation finally, okay, orientation of this can be expressed as that. Okay, so this is rotation about x axis by an angle, y axis and z axis. So it is known as, when it is all with respect to global coordinate system, that is with respect to earth or a fixed reference frame that is attached to the ground, it is known as roll, pitch and yaw. Rolling, you do rolling, right? You can do rolling. If ship can roll, okay, even flights can roll, right? In case of quadcopter or a drone, you can do that as well. So this is rolling. A pitching is doing this motion, okay, forward and backward. Okay, so about this axis you can do pitching, and yawing, right? Going left and right. Okay, so that is yawing about z axis. Okay, so you have roll axis, you have pitch axis, you have yaw axis. Combined together, you represent the orientation of an object. That is what is used in any mobile devices, let it be your cell phone or a gaming station or VR device that you may wear. Okay, quadcopter, flight, ships, everywhere. Okay, Formula 1 cars, industrial robots. That is where we are. Okay, so what we want to do, we want to express the end effector orientation. Okay, position, you know, you can directly obtain by connecting the base frame to the end frame using a vector, and that becomes its position. Okay, orientation is orientation expressed in Euler angle system using RPY system, that is normally preferred in case of industrial robots. Okay, so this is how it is. Finally, when you multiply that three matrices, okay, so this is rotation about x by this angle cos minus sin. This is rotation about y by an angle theta. This is rotation about z by angle phi. Okay, so three rotation consecutive given by this is RPY rotation. Okay, so that is what is a combined rotation matrix, which when applied to a point will take you to a new location which is rotated about x by this, y by this, z by this. Okay, three angles. Got it? So these are two different things. Okay, so now what is forward kinematics? Okay, what is forward kinematics? Basically, a robot goes to a pose means position and orientation, okay, by the effect of rotating individual joints. So this is first joint, this is another joint, is it not? You can rotate this, you can rotate this also by angle something, and then you can rotate about this axis, you can rotate about this axis, you can rotate about this axis. So you have 6 axis robot, so it combines with 6 different axes, 6 degrees of freedom robot. So all 6 joint rotations ranging from theta 1, theta 2, okay, theta 3, theta 4, 5 and 6, combination of all thetas, that rotation of joints gives you the end effector position. Link lengths are fixed. Okay, link lengths are fixed. The way joints are attached, they are also fixed. Okay, what is changing is only the joint angle through different actuators or the motors. Okay, so finally you reach to a position with certain orientation. You don't just reach there with respect to this, you just don't just go there, right? You also orient in a particular manner. Okay, so overall this is known as a pose. So when you change joint angle and you reach to a pose, that is combination of orientation and position, it is known as forward kinematics. Okay, steps for doing forward kinematics is basically you need to know what are link, what are joint and their parameters. Combinedly it is known as Dhanbad-Hardenberg parameter. So this is another convention which is being followed since long time now to represent a link and its shape and its relative position with respect to previous link. Okay, its relative position with respect to previous link. So it won't just define what is the structure of this link, any link, okay, what is the length of this, how much it is twisted, okay, rather it will also define how it is oriented with respect to the previous link. Okay, if this is the previous one, this can have certain angle with respect to that. So it also represents orientation with respect to that. Got it? So this is what is link and joint and their parameters. Let us say you have a link called as ith link. So how we'll go for it? So the previous link, this link will rotate. Let us start with rotation first. So this link will rotate about the frame which is attached to the previous link, is it not? So if this is the link, this will rotate with respect to this axis. This axis is placed on I minus 1th link. This is I minus 1th link. Okay, and this is its own joint. Okay, so normally DS parameter convention follows like you have to put all the axis or the joint with Z axis. So this is Z I minus 1. This is Z I minus 1. Okay, about which link I will rotate. So Zi minus 1 is the axis about which ith link will rotate. Okay, and this itself will end with the axis which is called Zi. So this will form the axis of rotation for I plus 1th joint. Okay, so forget this. So at least you have reached till here. Talk about just link 1, link I. Okay, so now what are things which are there? So there are 4 parameters. Okay, so first is this, you have to place Zi about the rotation axis, where you know link I is going to rotate about Zi minus 1 axis with respect to previous link I minus 1. Similarly, you have to place Zi, that is the basis of rotation for link I plus 1. So about that I plus 1th link will rotate. So you have two axes, Zi and Zi minus 1. So these are the two. Okay. Now, what are different parameters? First of all, let us say you have, if you can see my arms, so I have one arm, two arms, both are connected like this. Okay, both are connected like this. So these can rotate about one another. Okay, so this is your axis of rotation. You have an axis, you have an axis. So this is your axis of rotation. You have this another link that rotates like this. Okay, so what happens? So there is a offset between these two. What is that offset? If this is your link and this was earlier link, so there is some distance between them. So that is the distance that is known as offset and given by di. Di, that is offset. It is known as offset. So offset is the distance measured along zi axis, okay, and from the axis this. Okay, so you have two axes. Let me draw it more clearly now. Okay, I will wipe few lines now. Okay, so yes, so you have this and you have this. So you have a z axis which is like this. So this was zi minus 1. So this is the distance. So this is the distance given by di. Okay, so that is, this is your link length. What is link length? It is distance between two zi axis, that is zi and zi minus 1. Zi and zi minus 1. So common normal to zi and zi minus 1 is the link length given as link length. So this is your link length given as AI. Got it? So this is given as AI. So that is a common normal between Zi and Zi minus 1. Got it? Okay. So this is your link length. This is your offset. What is theta? Theta is the angle between two links. Okay. So if this was your earlier link axis, okay, and this is your new link axis, okay, link axis. So these two are common normal is link length, okay, distance between these two, and that becomes your xi axis. You already know where is your zi axis. Zi axis, that becomes the axis of rotation or translation. Okay, so this is zi axis, which is your link length. Link length is distance between these two, common normal distance, and that is your xi axis. So this is your xi axis. So now that you know zi and xi, So how can you obtain yi based on cross product, right? So it is zi cross xi. So this should give you y-axis. So y-axis is not very important here. If you know x and z, you already know y, and that is not used also in case of DS parameters. So normally these are the important parameters that 100% can define the structure of a link. So what are they? So this is your this. So this is your zi axis. This is your zi minus 1 axis. Common normal is xi. Distance traveled along zi minus 1, that becomes the offset of the link. So this is your offset, and this is your link length. This is your link length ai, and there is one more term, that is skewness, that is twist between zi and zi minus 1. So both the links are at a distance, okay, at a distance. So now both the axis, this link itself can be a twisted one, right? So that twist angle is rotation about xi axis, rotation about x axis by an angle alpha I. So that is known as twist. So twist is another parameter, that is basically angle between zi minus 1 and zi measured about xi axis. Got it? As a positive sense of rotation. Positive sense is always right hand thumb rule. Okay. So if this is your direction of xi axis, rotation about this as right hand thumb rule will tell you alpha I, that is angle between zi minus 1 and zi. So these are the four parameters which effectively completely defines the link structure. Link will have its length, link will have some angle of twist. That's all, that defines the structure. So once the structure is defined, it is never going to change. Okay, it will remain as it is. But what can change is basically joint angle, because you have second link rotating with respect to the first link using an motor which is fitted here, is it not? So definitely this will be your joint angle. Okay, so these are the four parameters which is very important. Okay, that defines the DH parameters. Basically DI, this is exactly the same in text. So if you have DI, what is DI? If this is your first link, this is your second link, a common normal, this is the axis of rotation zi minus 1 about which link I is rotating. So angle between them, this is your theta I, and offset, this is your offset, this is di. Di is the distance from the origin of I minus 1th link to ith link. Okay, so that is there. And then if at all this link also have, definitely it will have one axis that will be attached here, because that is the axis of rotation for the next link. Okay, this will be your theta I plus 1 whatever. Okay, if this is I, this will be I plus 1. Okay, so this is your zi. Distance between two zi's, common normal is link length given by ai. Got it? Common normal, this is your x axis also. So this is your xi. So xi is here, zi is already there, yi will be x cross z, z cross x. So this will be your yi, that is not very significant here. Okay, so this is your another frame. So first frame is here, another one is here. This is your offset, this is your link length, this is your joint angle, and there can be some twist. Both the z can be, there may be some angle between this, and that can be measured by rotation about xi axis, and that is given by alpha I, that is known as twist of that link. Hope it is quite clear. If not, you can revise this video once again and you can keep watching till you understand this. Try doing a line diagram. This is in text, I have written the same. Okay. Yes, so basically AI and alpha I, this defines the link length and twist angle. It is not going to change with time. That it defines the structure of the link, whereas di and theta I can be variable. Di, that is the joint offset. This link can move with respect to each other. Okay, two links can move with respect to each other. So first way of that is the rotation, that is the first way by which two links can be changed with respect to each other, right? So that is theta I if there is a rotary joint. If it is a prismatic joint, d also can change. Okay, so this defines the relative position of neighboring links. Okay, so that is the four parameters. Now looking at dh parameters, basically it is this is dh parameter. It will finally turn out to be a homogeneous transformation matrix that relates ith link coordinate system to I plus 1th link coordinate system. Let us go back to this. I have messed it out. Let me wipe it off. Okay. So this is your, these are your two frames. Okay. Now you have ended with two frames. One of the frame is now fitted here. Another one is here. So you have two frames. So DH transformation will basically be a link transformation matrix that represent ith frame. This is your ith frame with respect to I minus 1th frame. So ith frame with respect to I minus 1th frame. So this will be a combined transformation which represents ith frame with respect to I plus I minus 1th frame. So that will be your link transformation matrix. Okay. So that is your DH transformation. Okay. Okay. So that is basically a 4 cross 4 homogeneous transformation matrix that relates ith link to I minus 1th coordinate system. Link here I mean link frame, the frame which is attached to the ith link. Okay. Okay, now how this is done basically. So first you rotate, let me just go there and see. Okay, first what you did, this was your link first and this is your link second. Okay, so both of them have some angle with respect to each other, that is theta I. So because this was zi minus 1, this is rotation about z axis. Okay, so that is the first thing that you do. Another one is, if this is your first link, this is your second link, and this is your common zi minus 1 axis, so there is an offset, this is di. So first go, if you want to reach from here to the ith frame, so this is I minus 1th frame which is attached here, ith frame is attached here. So in order to go from here to here, what all transformations that are required? First transformation is translation x, y, z, translation along z axis by a distance di. This is first transformation. Okay, translation along zi minus 1 by a distance di first. Next is rotation. If you look from the top, there is rotation by an angle theta I, and this is your zi minus 1 axis, is it not? So rotation about zi minus 1 axis by an angle theta I. So this is rotation about z by angle theta I, is it not? So that is your second transformation. You reached from this location to this location now. Okay, and now you have a frame. Now what you will do, next one will be translation along x axis, xi axis by a distance ai. So you see, it is translation about x axis, along x axis by a distance ai. Why is it so? Because this was your relative position, this is your zi minus 1 axis. Okay, and this is where you were, this much you have already done, you have already rotated by an angle theta I. Now you can move along x axis, xi axis. This was your zi, if you remember. So this is the distance that you want to move. This is the distance that you want to move, and in which direction? It is along x axis. So distance moved along x axis by a distance ai. So this is your link length. Okay, this is the third transformation, and the fourth one is the twist angle between zi and zi minus 1, that is the rotation by an angle alpha I, and this rotation will be about xi axis, is it not? So now finally you see you have a transformation matrix, that is a rotation transformation. This represents rotation about x axis by an angle alpha I, right? If you remember this, so it was rotation about xi by an angle alpha I. Finally you reached to this point. Okay, so you have to reach from here. So four transformations. First is translation from here to here, next rotation, next translation, and again rotation. Four transformation, and you reached from here to here. So this will represent four different transformations so as to reach from a link this point to this point of that link, is it not? First frame to the next frame, then you can keep moving from this frame to this frame, this frame to this frame, so you can keep on moving till you reach to the end. So this is how you do forward kinematics. So this is your four transformation which were done first, second, third, fourth. You have to do post multiplication because it is on the on top of where you are already. Okay, you are not doing a global transformation. Okay, so this is your four transformation that you have done. Multiply them, you get a link transformation matrix which effectively takes you from this link joint to the this link, this point. This is I plus ith frame, and this is your I minus 1th frame. Okay, so you have reached from here till here. So this is your transformation matrix. So effectively this is the transformation that takes you from this frame to this frame. Okay, and you can keep on doing that, concatenate that transformation, and we do forward kinematics. So you multiply them all together. So you keep on moving from robot base, that is 0 to 1, 1 to 2, 2 to 3, and so on so forth until you reach till the end. Okay, so that is the ith link. So that is what I have done. So 0 to 1, 1 to 2, 2 to 3. Finally you take the product of all those, and what you get is a final transformation matrix of the end effector point. Okay, so what this will have? We started from here, which was a frame located at 0, 0, 0. If I keep on translating that and taking it to this point, effectively this will give me what? It will give me position of end effector. Okay, so this is basically the position, that is the position t vector. Okay, t, that is this t vector, and orientation of the end effector frame. It will have its own orientation, is it not? So that is given by rotation matrix NOA, if you remember. So this is the frame projection of those. This is the three projection of the end effector frame along global XYZ frame. So this is your rotation matrix that represents the orientation, and this is your position. Got it? So effectively we use joint symbols as this: rotary joint, prismatic joint can go like this. Okay, standard frames, this is your standard coordinate convention that we'll be following also, and this is your standard way of representing any rotation, positive direction of rotation. Okay, so yes, this is the step to assign DH frame. We'll do using one of the robot, that is Yaskawa GP12 robot today. Okay, so hope this is quite good enough as a fundamental now. Okay.